Section: Introduction. In this section, we delve into the advancements and challenges associated with large language models, LLMs, particularly in their ability to understand and generate text in a manner akin to humans. We've observed that by increasing both the size of these models and the amount of data they're trained on, LLMs have become more adept at predicting the next pieces of text and executing tasks with minimal examples. Despite these improvements, there's a noticeable gap in their ability to follow human instructions accurately. To address this issue, we explore the concept of instruction tuning, a method that fine-tunes LLMs using instructions paired with responses that are preferred by humans. This approach has traditionally relied on either seed examples or existing datasets. Initially, we used datasets from the field of natural language processing, NLP, described through instructions, to fine-tune LLMs. These fine-tuned models showed promise in generalizing to NLP tasks they hadn't seen before. However, the limited number of NLP tasks available restricts the model's ability to generalize in more diverse real-world scenarios. We then introduce self-instruct, a cost-effective strategy for creating synthetic instruction tuning datasets. This method begins with a small collection of human-written seed instructions and expands it by prompting an LLM with a selection of these instructions. Despite its efficiency, we've found that the diversity of the generated instructions is limited, as the model tends to produce instructions that are too similar to the examples it was given. Moreover, crafting high-quality seed instructions demands significant human effort and expertise. To improve upon self-instruct, we developed Evolve Instruct, which enhances existing instruction tuning datasets through various rewriting operations performed by LLMs, essentially augmenting the data. However, the diversity of tasks and domains these augmented datasets can cover is still constrained by the original datasets. We also acknowledge studies that focus on developing instruction tuning datasets for specific domains or tasks, such as mathematical reasoning or coding-related tasks. Yet, these methods fall short of producing instruction datasets that are broadly applicable across a wide range of domains. In our quest to create a general instruction tuning dataset, we draw inspiration from the structured approach of the human education system, which encompasses several levels, from early childhood education to higher education and beyond. This system allows students to systematically acquire a wide range of knowledge, skills, and values. We believe that mimicking this structured approach can aid in generating high-quality and general instruction data across various disciplines. In this paper, we introduce a new paradigm called GLAN, Generalized Instruction Tuning for Large Language Models, for generating synthetic instruction tuning data almost from scratch. Unlike previous methods, GLAN leverages a pre-curated taxonomy of human knowledge and capabilities, systematically generating instruction data across all disciplines. This taxonomy is constructed by breaking down human knowledge into fields, subfields, and disciplines, with the help of LLMs and human verification. The verification process is efficient due to the taxonomy's limited scope. We further detail how we break down these disciplines into smaller units, generate a comprehensive list of subjects for each discipline, and design tailored syllabuses using LLMs. By focusing on the key concepts in each class session of the syllabus, we can generate diverse instructions that cover a broad spectrum of human knowledge and skills. GLAN stands out for being general, scalable, and customizable. It is task-agnostic, capable of covering a wide range of domains, and can generate instructions on a massive scale with minimal human effort. Additionally, GLAN allows for easy customization by adding new fields or skills to our taxonomy. Through extensive experiments with large language models, such as Mistral, we demonstrate that GLAN excels in various dimensions, including mathematical reasoning, coding, academic exams, logical reasoning, and general instruction following, without relying on task-specific training data. Section Summary. In this section, we introduce a method called GLAN, Generalized Instruction Tuning for Large Language Models, that aims to create synthetic instruction tuning data across various disciplines systematically and automatically. By leveraging a pre-curated taxonomy of human knowledge and capabilities, we break down disciplines into smaller units, design tailored syllabi for each subject, and generate diverse instructions covering a wide spectrum of human knowledge and skills. GLAN is task-agnostic, scalable, and customizable, allowing for easy addition of new fields or skills without the need to regenerate the entire dataset, showcasing superior performance across multiple tasks without task-specific training data. Section: GLAN, Generalized Instruction Tuned Language Models. In this section, we introduce GLAN, which stands for Generalized Instruction Tuned Language Models. Our goal with GLAN is to generate a wide range of synthetic instruction data that spans various areas of human knowledge and skills on a large scale. To achieve this, we start by creating a detailed classification system, or taxonomy, of human knowledge and capabilities. This involves using advanced language models like GPT-4, along with human checks, to ensure accuracy and comprehensiveness. This taxonomy helps us organize human knowledge into broad categories, which are then divided into subcategories and specific disciplines. Once we have our taxonomy, we move on to breaking down each discipline into a list of subjects. We do this by instructing GPT-4 to act as an educational expert for each discipline and come up with a list of subjects that students should learn. This process results in a comprehensive list of subjects, including details like the level of difficulty and main topics covered, although initially in an unstructured text format. To make this information more usable for our next steps, we convert it into a structured format, specifically JSONL, through another round of prompts to GPT-4. This step ensures we have a detailed and organized list of subjects for each discipline. Next, we focus on creating a syllabus for each subject. This involves further breaking down each subject into smaller units, making it easier to design homework assignments. We ask GPT-4 to create a syllabus that outlines the main topic of the subject, divides it into class sessions, and details the key concepts and subtopics that need to be covered in each session. The syllabus also includes the objectives and expected outcomes for the subject, which are crucial for generating homework questions. Although the syllabus is initially generated in an unstructured text format, we extract the names of class sessions and the key concepts for each session in a structured format, similar to how we handled the subject list. By systematically breaking down human knowledge and capabilities into smaller, manageable units and converting this information into structured formats, we prepare the groundwork for generating synthetic instruction data. This data, which includes homework questions based on various class sessions and key concepts, aims to cover a wide range of topics and ensure diversity in the instructions. Our approach ensures that the instruction data we generate is both comprehensive and adaptable, capable of evolving as the capabilities of language models like GPT-4 continue to advance. Section Summary. In this section, we aim to create synthetic instruction data covering various domains of human knowledge and capabilities at a large scale using GLAN. We build a taxonomy of human knowledge and capabilities by breaking them down into fields, subfields, and disciplines, and then instruct GPT-4 to design syllabi for each subject, which further decomposes into class sessions with key concepts for students to master. By recursively decomposing human knowledge into smaller units and generating homework questions based on class sessions and key concepts, we ensure the diversity and coverage of synthetic instructions. Section: Instruction Generator. In this section, we discuss how we go about creating homework questions and their answers using a given syllabus, a list of class sessions, and their associated key concepts. To start, we select either one or two names of class sessions from the list and choose between 1 to 5 key concepts from those sessions. We refer to these selected class sessions as selected class sessions, and the chosen key concepts as selected key concepts. With these selections, we then ask GPT-4 or GPT 3.5 to come up with a homework question that incorporates the selected class sessions and key concepts, along with the overall syllabus. Our goal is to provide GPT 4.5 with enough context, such as what students have learned in previous sessions, to create meaningful assignments that integrate multiple key concepts from different class sessions. When it comes to choosing class sessions and key concepts, we employ two strategies. The first strategy involves focusing on a single class session and randomly selecting 1 to 5 key concepts from it. This approach allows us to create basic homework questions. The total number of possible combinations of key concepts we can choose from is calculated using a mathematical formula that considers all possible selections of 1 to 5 key concepts from the total available in that session. For a more challenging approach that combines knowledge from multiple class sessions, our second strategy involves selecting key concepts from 2 different class sessions. This method significantly increases the number of possible combinations of key concepts, allowing us to generate questions that require a broader understanding and integration of the material. The exact number of combinations in this case is also determined by a mathematical formula that accounts for the total possible selections of 2 to 5 key concepts from the combined pool of key concepts from both sessions, subtracting the combinations that only involve key concepts from one session or the other. After generating the questions, we use GPT 3.5 to create answers for them. We prefer GPT 3.5 for this task because it provides sufficiently high-quality answers and operates faster than GPT-4. The questions and answers we generate form a set of instructional materials that we use to fine-tune the language models. With a vast array of question-answer pairs covering various subjects and difficulty levels, we aim for the resulting language model to excel across a wide range of tasks. In our experiments, we also work on creating a taxonomy of human knowledge and capabilities by asking GPT-4 for input. We then refine this taxonomy with the help of human annotators to ensure it's both comprehensive and not redundant. After a majority vote, we decide on keeping 126 disciplines, though we remain open to manually adding more as needed. For generating subjects and syllabuses, we rely on GPT-4 and use specific settings to encourage diversity in the subjects we create. We query GPT-4 multiple times for each discipline to ensure a wide range of subjects, acknowledging that some subjects may overlap across disciplines, which we see as an indication of their importance. Each syllabus we design includes a variable number of class sessions, each with about 5 key concepts, to ensure a comprehensive educational plan. Section Summary. In this section, we generate homework questions and answers by sampling class sessions and key concepts from a syllabus. We use 2 strategies. One focuses on a single class session for basic questions, while the other combines key concepts from 2 sessions for more challenging questions. After generating questions, we employ GPT 3.5 for answer generation, resulting in a diverse set of question-answer pairs for instruction tuning data, aiming to enhance the performance of the resulting LLM across various tasks. Section: Instruction Generation. In this section, we discuss how we create instruction data, which includes both a question and its answer. We decided to generate questions and answers separately because we noticed that doing so leads to higher quality results. For generating questions, we use GPT-4, and for answering them, we opt for GPT 3.5 Turbo. When using GPT 3.5 Turbo, we set the temperature to 0.7 and the top P to 0.95. This lower temperature helps make the answers more precise. We chose GPT 3.5 Turbo over GPT-4 for answering questions because it's much faster and still delivers reasonably good results. In total, we generated 10 million pairs of instructions and responses. Then, we cleaned up the training data by removing any pairs that included questions or prompts from the test sets or training sets of the benchmarks we're evaluating. This step ensures that our synthetic data can be generalized well. For training our model, we use Mistral 7B as the base model. We combine each instruction and response into a single sequence but only calculate loss on the response part. We train the model for 3 epochs with a learning rate of 3 × 10⁻⁻⁶. The batch size we use is 512 pairs of instructions and responses. Our learning rate follows a cosine schedule, starting with a linear warm-up of 1,000 steps before reducing to 0. When it comes to evaluating the effectiveness of our instruction data, we cover a broad range of subjects. This includes mathematical reasoning, coding, logical reasoning, and academic exams. For mathematical reasoning, we test our model, GLAN, using two popular benchmarks to assess its ability to solve basic and complex math problems. These benchmarks are the grade school math word problems and the mathematics aptitude test of heuristics dataset, which include problems from various math competitions. In the coding domain, we evaluate GLAN's coding capabilities using two benchmarks, Human Eval and MBPP, employing different settings based on previous studies. Additionally, we assess GLAN's general reasoning abilities on the Big Bench Hard dataset, which includes 23 challenging tasks. For academic exams, we test GLAN on benchmarks consisting of multiple-choice questions in science and a wide range of other subjects. These benchmarks are the AI2 Reasoning Challenge and the Massive Multitask Language Understanding. Notably, we exclude any training set data from these benchmarks during our decontamination process to ensure our model's ability to generalize. Unlike previous models that mostly rely on probability-based methods to select the best answer, GLAN generates predicted options and analyses in plain text after being trained on 10 million homework questions. Our results, detailed in a table, show that GLAN performs exceptionally well or close to the best across all benchmarks when compared to general domain models, math-optimized models, and coding-optimized models. We also include results from base language models for reference. We observe that after instruction tuning, GLAN excels in various areas, demonstrating the effectiveness of our systematic data generation approach. Importantly, our method does not rely on any task-specific training data, highlighting GLAN's broad applicability. Section Summary. In this section, we generate instruction response pairs by creating questions and answers separately for better quality. We use GPT-4 for question generation and GPT 3.5 Turbo for answer generation with specific temperature and top p-values. Our model training involves Mistral 7B as the base model, training for 3 epochs with a learning rate of 3E6, and evaluating GLAN's effectiveness in mathematical reasoning, coding, logical reasoning, and academic exams across various benchmarks without using specific training data for those tasks. Section. A closer look at academic exams. In this section, we delve into a detailed examination of academic exams, focusing on multi-choice-based benchmarks such as ARC and MMLU. We've noticed that our model, GLAN, shows significantly better performance improvements over Mistral on the ARC benchmark compared to MMLU. When we categorize the 57 subjects in MMLU into 4 groups, STEM, Humanities, Social Sciences, and Other, which includes business, health, and miscellaneous, it becomes clear that GLAN particularly excels in STEM subjects within MMLU, but not so much in the other categories. It's also worth mentioning that ARC consists of high school science problems, which fall under the STEM category. The reason GLAN performs well in STEM subjects might be because the responses in our dataset come from GPT 3.5 Turbo, which is designed to generate responses using a chain of thoughts, COT, reasoning approach. Indeed, we've observed that GLAN tends to generate solutions using COT for multi-choice questions. This COT approach is likely beneficial for the multi-step reasoning required in STEM multi-choice questions, whereas questions in humanities and social sciences might rely more on memorization and single-step reasoning, where COT could potentially introduce errors. Moving on to task-specific training data, GLAN represents a generalized method for creating synthetic data for instruction tuning. To test the generalization capabilities of this synthetic data, we intentionally left out task-specific training sets from all benchmarks in our assessments. Similar to previous studies, we investigated whether models had been trained on task-specific and domain data. We calculated the training loss and test loss on several datasets, including ARC Challenge, ARC Easy, GSM 8K, and Math for GLAN and other models for comparison. We chose these datasets because they contain training sets. Intuitively, the larger the difference between test loss and training loss, the more likely it is that the training set was exposed. To make this difference easier to interpret, we also calculated the relative difference as a percentage. Our findings show that the losses for GLAN on both training and test splits are nearly identical, or even negative in some cases. This suggests that GLAN was not exposed to in-domain data during its training and tuning processes. Additionally, we observed that GLAN incurs higher losses on both test and training splits on these datasets compared to other models, yet the performance of GLAN on these datasets remains high. This could indicate that the synthetic data generated by GLAN is diverse, and our model avoids converging to any specific domain or style present in existing benchmarks. Regarding the instruction following evaluation, IF-eval, we assessed GLAN's ability to follow instructions using the IF-eval dataset, which consists of a collection of verifiable instructions across 25 distinct types of instructions, totaling around 500 prompts. Each prompt includes one or more verifiable instructions. The evaluation uses 4 types of metrics at both the prompt level and instruction level, assessing both strict and loose accuracies. Our findings show that GLAN demonstrates superior instruction following capabilities in both prompt level and instruction level evaluations, although there is still a significant gap when compared to GPT 3.5 Turbo and GPT-4. Lastly, in the EVAL Instruct test, which contains real-world human instructions from various sources and consists of 218 instances with 29 distinct skills, each instruction is associated with a difficulty level from 1 to 10. The responses are often open-ended descriptions, making this benchmark a necessary supplement to IF-eval. Following previous methodologies, we used a GPT-4-based automatic evaluation method for a pairwise comparison between GLAN and other models. GPT-4 was instructed to assign a score based on the helpfulness, relevance, accuracy, and level of detail of responses generated by 2 different models for a given input question. To avoid potential order bias, we conducted bidirectional comparisons for each response pair and calculated their average score. The results of these pairwise comparisons across various levels of instruction difficulty show that GLAN outperforms other models, including Llama 2, Orca 2, Mistral Instruct, and even WIZARDLM13B, despite GLAN having only 7 billion parameters. This indicates that GLAN has an improved ability to process diverse instructions, regardless of their difficulty or complexity. However, it's important to note that GLAN still lags behind GPT 3.5 Turbo and other models in comparison. Additionally, when we grouped the EVAL Instruct test according to the 29 skills, we observed similar trends. GLAN shows strong performance on most skills, especially in math, coding, and reasoning, but falls slightly short in tasks related to common sense. Detailed results of this analysis can be found in the appendix. Section Summary. In this section, we examine the performance of GLAN on academic exams like ARC and MMLU, noting significant improvements over Mistral on ARC, particularly in STEM subjects. GLAN's strength in STEM may be attributed to its use of GPT 3.5 Turbo, which aids in chain-of-thoughts reasoning for multi-choice questions. Furthermore, by excluding task-specific training data, we find that GLAN's synthetic data generation approach leads to diverse models that excel in instruction following evaluations like IF-eval and EVAL Instruct tests, showcasing superior performance across various difficulty levels and skills compared to other models. Section: GLAN test. In this section, we discuss the limitations of existing instruction evaluation tests, such as IF-eval and EVAL Instruct test, which only include a few hundred instructions and cover a limited range of domains or skills. To address this, we introduce a new test set derived from GLAN data, which we refer to as GLAN test. This test set is comprehensive, containing 6,300 instructions across 126 disciplines, with each discipline receiving 50 instructions. We've organized these disciplines into 8 distinct fields, including various academic areas like humanities, social science, natural science, applied science, formal science, and industries like manufacturing, services, and agriculture. We believe that the broad domain coverage of GLAN test makes it an excellent tool for evaluating the generalization capabilities of large language models, LLMs. For our evaluation, we follow the same protocol used in the EVAL Instruct test, utilizing GPT-4 to conduct a pairwise ranking of GLAN against other models. The results, detailed in a table in the paper, show that GLAN outperforms several other models, such as Orca 2-7b, Mistral 7b Instruct, and WIZARDLM13b, despite all these models having around 7 billion parameters. However, it's important to note that GLAN still falls short when compared to GPT-4. For those interested in more granular results, we've included detailed performance data for the 126 disciplines in the appendix. Our findings highlight GLAN's effectiveness across multiple domains, such as mathematics, physics, chemistry, computer science, electrical engineering, and mechanical engineering, suggesting that even smaller models can achieve general improvements across various domains through strategic fine-tuning. However, we also observed that GLAN's performance is not as strong in certain areas, like American history, divinity, and radiology, indicating room for further refinement and development in these areas. In the related work section, we explore how recent studies have gathered various human-made resources for instruction tuning. Some approaches involve collecting existing natural language processing (NLP) datasets and their task descriptions, training models like BLOOMZ and FLAN with this data. However, the diversity and scope of instruction tuning are somewhat limited due to the relatively small number of available datasets. Another approach involves using real-world human user prompts for instruction tuning, as seen with Instruct GPT, Vicuña, and DALL-E. While this method can provide high-quality instructional data, it often comes with high costs and privacy concerns. As LLMs continue to improve, instruction tuning using LLM-generated data shows promise for scalability and addressing the super-alignment problem. By leveraging the in-context learning capabilities of LLMs, methods like unnatural instructions and self-instruct use seed instructions to prompt LLMs to generate new instructions. Similarly, models like Wizard LM and Wizard Math are trained using Evil Instruct, which iteratively employs ChatGPT to rewrite seed instructions into more complex ones. Despite these innovative approaches, challenges in generalization remain, as the diversity of the training data is limited by the initial seed instructions or topics.